Hi, Bobby. So, just to refresh your memory on what we did in the last couple of lectures, we looked at the sinusoidal wave, especially the 50 hertz supply that we get in our sockets,
Okay,
right?
okay,
So, we
correct.
saw this wave. So, we said V of t is some VPP sine of omega naught t.
Okay.
Okay, and omega naught was 2 pi by t. So, the 1 by t is the 50 hertz that we are talking
Frequency.
about. Yes,
Okay.
right? And the VPP is, I remember you telling me that when you connect your the multimeter into the socket, you see the RMS
True.
voltage, right? So,
Correct.
this VPP was going to be some root 2 times 230
Root 2 times RMS voltage.
RMS voltage, right? So, that was the peak to peak voltage. So, if you plotted this, you would find something like this, right? This is T by 2, and of course, this is a periodic signal with time period
T.
right? So, what happens is, if you plot this, you will see a wave, a sine wave like this, okay, and this of course will continue forever like this and so on.
So its peak is VPP.
Yes, the peak is going to be VPP and the
Of course, minus will negative side minus VPP.
exactly negative side is going to be minus VPP, absolutely. But the question is, are these two parameters, the amplitude and the frequency, is it sufficient to characterize a sine wave?
Maybe for one sine wave, maybe enough. Or see, I was working in some circuit where I was observing voltage, current, many currents and so on.
Okay.
Then I was trying to keep one waveform on top of the other. The waveform looks similar, but it's not on top of the other one, is shifted by a little bit.
Oh, so you're saying what you observed was an other waveform, something like this?
Yeah, something like that. It's not exactly on top of the other,
Okay.
but same shape, same time period T, VPP is same.
Okay. So if you look at this, this wave, it comes back like this, and so at t equal to 0, it is already at some minus
Value.
some negative value.
Correct.
Right?
Correct.
Some minus a. Okay. So how do you capture this information? So you're effectively saying there is a delay between two sine waves,
Yeah.
but they are of the same frequency, same amplitude.
Yeah.
Right?
So the same peak is happening after some time or
After
before
some
some time with respect to the original one you have drawn.
Okay. So, so can we capture that?
In time information maybe?
Yeah, in time in as sine of omega naught t plus phi.
So phi being that extra. Okay,
Yeah,
okay.
right. So at t equal to 0, we already know, for example, this magenta wave at t equal to 0, the value is VPP sine phi,
Okay.
right? So in this case, if I just say VPP sine of phi equals minus a.
Okay,
Then-
so this is what this phase or something?
Exactly.
Okay.
This is called a phase. So you have amplitude, frequency and phase. The phase just tells you how delayed that sine wave is with respect to the original one. Just like you mentioned here.
It can come in advance also.
Yes, it can come in advance. In
Okay.
fact, if if we look at this example here, right? So maybe we should plot something very specific, right? So this is time. Okay, this is as usual t by 2 and t. Okay, so let's look at a sine omega naught t. Okay, and the second one I want to look at is a sine omega naught t plus pi by 2.
Plus pi by 2.
Plus pi by 2. Okay, so effectively the black one is obviously going to start at 0, go down like this, and it will keep going on like this. The magenta one at t equal to 0 is already at 1
Okay.
or at A, right? So if you look at this wave is going to start, you know, somewhere here. It is going to
At
hit
0 you have maximum.
Yes, so
When
it's
time
this
t goes
entire thing is shifted back. So 0 to t by 2 is going to go backwards, and so if you look at this, right?
Maybe we can just draw there.
Yeah, so this is t by 4. So at t by 4 the original wave is hitting 1, right? But at 0 itself this magenta wave is hitting the maximum, right? So therefore this has to be shifted back by an amount of t by 4, right? So effectively if you look at the magenta wave, it would be, you know, from minus t by 4. So let me just redraw this. Okay, the magenta is going to start at minus t by 4 like this, come down here, and so on.
Okay. So this is like same phi that you have marked earlier, but plus phi.
Yes, exactly. So it is plus pi by 2. Now I could have omega naught t minus pi by 2, right? In which case the minus A would happen at 0, right? So in which case that would get shifted by minus, you know, t by 4, okay? So effectively this is what the concept of phase is.
So when the phase is negative, it's like it's lagging.
Yes, it's lagging. When it is positive, it is leading.
Leading.
Exactly,
Okay.
right? So
With respect to some reference.
with respect to the original one, which is defined as 0 phase.
Okay. Okay.
Okay. So you know, the concept of adding sinusoids and sinusoids with phase shifts is something very common in electrical engineering that we will look at a little later. Right. So now, you know, having described a sine wave completely, we also have to look at another interesting idea. So, you know, you have looked at the voltage, right? From
This 230 volt,
230
50
volt,
hertz sine
right?
wave.
Exactly. Have you tried observing the current?
Yeah, actually, you know, some loads when we connect, mostly power electronic type of load, and I was observing the current just out of curiosity. Is it really sine wave?
Yeah.
Then I see some little bit distorted sine wave. The current.
Okay. So, right. So, this is actually a great question, and I don't know the specifics of this case, but in general, if you have some sort of a non-linearity in your system, you would end up with what is known as a harmonic.
Harmonics?
Yes, harmonic.
Means?
Okay. So, that's why I brought my violin today.
Oh, so you are pre-planned.
Yes.
Okay.
Indeed. Okay. So, what you see is, you know, if you observe this string very carefully, it is pegged here.
Correct.
And it is pegged at this point.
So there is a fixed length.
Yes, there is a fixed length, and if I cause this to vibrate, there is a certain frequency that we hear, or a certain note that we hear. I should not say frequency, right? Now, what do you expect that note is?
It may have to something to do with the length, because if I change the length, it is changing.
Exactly, right? So if I, for example, you know, keep it here, it changes, right? If I go here,
yeah, correct,
right?
Yeah.
So clearly the length is actually causing a change in the note that we hear, right? But what is this note? Is it just one frequency that you're hearing?
See, I was trying to compare with this tuning fork. Tuning fork, I hear very sharp
Exactly.
sound. It's a bit different here.
Exactly. So a tuning fork is supposed to give you just one frequency, and that is a very, very sharp tone, as you say.
Correct.
Right? But here it's not like that. It's not a very sharp tone. It seems to be some combination of things. Right?
So it's not just one thing. Okay.
It's not just one
please.
thing, right? So I think let's, to understand this a little better, we have to go back to our simple harmonic motion and waves, okay, before
Sure.
So let's start.
If that helps, let's see.
Exactly. So let's say there are some air molecules like this, okay? And how does this air, how do you listen to the sound and all that? So there is some vibration that we set, right? And these air molecules are all vibrating together in a certain pattern, right?
And that is
Exactly.
hitting
and that
on
is
our
coming
diaphragm.
exactly to your ear, the cochlea and all that, and that's how you process it, right? Now, how do these air molecules vibrate? So if you look at this, each of them, right, is simply executing what is known as simple harmonic motion. Simple harmonic motion is the displacement is some sine omega naught t, okay? So each of these y of t is exhibiting some simple harmonic motion, sine of omega naught t, but not with the same phase.
okay.
Okay, so I will in fact call this phi x. Okay, so if you look at this as a function of the distance, right, there is a certain phase associated with each of these air molecules.
Okay.
So, and that is given by this A sine omega naught t minus kx. Okay. So, what is k? It is 2 pi by lambda, and lambda is known as the wavelength. Right? Now, what is omega naught? That is related to time, right, or the frequency. So, this is 2 pi by t naught,
Yeah.
right, where t naught is the
Time period that you
frequency.
Okay.
Other correct, you're right, it's a time period.
Yeah.
Yeah, in the case of the supply voltage, it was at 1 by 50 hertz, right? So now, so what is going to happen is, if you just freeze all these oscillating particles, right, that is partaking in this wave propagation, right? If you just freeze it at a certain time and observe where these particles freeze, right, you will see that this particle might freeze exactly at 0. This particle might freeze slightly away from 0. This particle further away from 0. This particle further away, right? This further, then it starts coming back. Okay, so what am I calling as y of t here? I'm calling this displacement
Okay.
from the center as y of t. So the air molecules are vibrating in the direction in which the wave is going, right? In electromagnetic waves, by the way, in electrical engineering, electromagnetic waves, the vibration happens in a perpendicular plane, perpendicular to the direction of flow of energy. Whereas here the vibration is happening in the direction of the flow of energy, right? So what we are looking at now is, if you take this y of t, okay, and you simply plot it, okay, as a function of x, you will get some wave like this. Okay, I am now talking of y of x here. So you have y of, this is not just y of t now, by the way, this is y of x comma t actually, because it's both a function of, you know, the space
And
time. Okay, so here this is going to be your lambda by 2 and this is going to be lambda.
Oh. But this lambda and this length has
Exactly,
Okay.
right? So this lambda and the distance length of that string which is going to vibrate has a certain relationship. So what I'm driving home here is that if you take this, so like I said, you first freeze time, okay, and then look at this as a function of x.
Okay.
Okay, you are going to get a certain sine wave which is going to repeat. Now, if you freeze x, right, if you freeze x, just pick this air molecule and observe it as a function of time, that will be executing simple harmonic motion about its mean, and just it will keep vibrating as a function of time. That's all. So there is another sinusoid with respect to time there.
Okay.
There is another sinusoid with respect to displacement here, right? Now, if I want the wave to propagate fast, right, then the next molecule has to have a larger displacement if it wants
in a given time,
right? Then it moves faster, right?
Okay.
So, in some sense, the velocity of the wave is the wavelength into the frequency f naught, or it is the wavelength divided by the time period, right? So, in what I am trying to say is this frequency and wavelength are related to a velocity of propagation, and usually the velocity of propagation is determined by other factors in a medium. For example, light has its velocity in free space as 3 × 10⁸ meter per second, but in glass, because of refractive index, there will be a change and so on, right? So usually these things are all related, and this relates your velocity, wavelength and frequency.
Okay.
Okay. So now let me come to the point of the violin that we were talking about. Okay. So I am now talking about the case where we have a string that is clamped at both ends, and I have a string which is like, of course it has to be tight, it has to be, you can also derive an equation for the frequency of vibration and all that, right? But if you remember this tuning fork experiment that you spoke about, if for a certain frequency, if you bring it close by, you will see that because of resonance, this thing starts vibrating. Now, what are the allowed modes of vibration, right? Can this oscillate in any frequency? Why doesn't it respond if I bring another tuning fork of a different frequency? Like maybe 440 Hertz, it might not resonate. 512 Hertz, it will resonate, right? So what is special about 512, 440? Why not for 440, right? So here I am talking about x equal to 0, x equal to L.
Okay.
Okay. Now what is going to happen is, because the string is clamped at both ends, when a standing wave is set up, it has to be like this.
Standing wave?
Yes.
What is that?
So you have an incident wave, a reflected wave, and together they basically give you a standing wave. So I mean, I will not go into those details because they have been done in 11th and 12th.
Okay.
Just for now, I just want to drive home a certain idea that is easily, seen from here. Okay. So you have the first case where, if you remember this, this case when I drew this thing, right? The sinusoid as a function of displacement.
Yeah.
Right? This was lambda by 2 and this was lambda.
Correct.
Right? So it's going to go, so here this length is fixed.
Yeah.
Okay. And this is going to be lambda by 2.
Uh-huh.
So this is the first allowed mode of vibration for this string. Okay. So I say lambda by 2 equal to L. Okay. Which implies this lambda is going to be 2 into L.
Okay. But this is not the only mode.
This is not the only mode, right?
Otherwise, I should have here just
exactly.
tuning fork
you should have
equivalent sound.
Only that. Now, let's say this responds to a tuning fork of a certain frequency. If you now bring, let's say 512 Hertz, I bring now 512 into 3, right? Something interesting happens there. Even then this guy will respond. So why is that? That is because it is possible to have another wave like, no, sorry, not like this actually. let me just redraw this. Okay, the first case was like this.
Yeah.
Okay, the second case is like this, right? It is possible for me to have the two ends being 0, but an entire wavelength
Is
now
in that
is accommodated in that
length
particular,
itself.
yes, in that particular length, right? Which implies here lambda equal to L, right? So I would say, so this is the fundamental mode. Right? And this guy is the second harmonic.
Oh. Oh, so this is the harmonic that you are referring to.
That I was talking about. So when we hear something like this, it's not just that one frequency, it is the frequency and its harmonics that we will invariably hear, right? And similarly, I could
What about the height? Fundamental and harmonics almost same height, or?
Oh, so that is a very good question. Usually the harmonics will be diminished, right? Will be diminished in amplitude. The energy of the harmonic will not be the same, right? So this is the first one. Now the third case is I could have where I have 3 half wavelengths, right? Where I am saying 3 lambda by 2 equal to L. Okay, so now you can also go back and relate that original equation. The velocity, right, is lambda into frequency. Okay, so if the velocity is the same, then lambda 1 f1 equal to lambda 2 f2 equal to lambda 3 f3. Okay, so here if you look at what's happening, in one case lambda was 2L into f naught. That is my fundamental, is what I called as fundamental. The next one is lambda is L, so L into f1, right? And what is this here? Sorry, this is 2L, not 2L, right? And the third case is the wavelength, right, is going to be 3 lambda by 2 is the L, right? Therefore, the wavelength is going to be lambda is going to, in this case, lambda is going to be 2L by 3.
Yes.
Right? So here I will say 2L by 3 into F3. Right? So this is, I can write this second one, right, as 2L by 2. Right? So clearly you can see that the frequency F1 2L by 3, right, implies F1 equal to 2F0 and F2 equal to 3F0. So the fundamental frequency is there.
That is F0.
F0. The second harmonic is going to be twice F0. The third harmonic is going to be this guy. Let me just write that as F2. This is the third harmonic. Okay. So in some sense, we always have to deal with the fundamental and its associated harmonics. And as you said, the energy and the amplitude of the harmonics will drop.
Mostly.
Yeah, with time and with this thing. So depending on the system, but you have to know how to analyze harmonics and frequencies, right? So we don't have to worry about 1.5 F0 or 2.3 F0. That is not going to happen in many cases. Okay, so if you wanted to sort of come back to an electrical, more an electrical engineering analogy, right? It would be essentially.
So what I have seen in the current is combination of all this.
What you have seen is a combination, and why is that? Mostly if you have a non-linear system, yes, right? You give x of t, okay, and you.
So far we have shown resistor, etc.
Yeah,
it's not a resistor.
Those are not nonlinear systems.
Correct.
Those are linear systems, resistors, inductors, capacitors. Because if you give a combination of inputs, you will get a similar combination of outputs, right? So a linear combination still remains. But here if I give, let's say I get x squared of t. I give x of t, I get x squared of t.
Okay.
Right? Then invariably if you give a sine omega naught t, you will end up getting a squared sine squared omega naught t.
Okay.
Right? Which
so that system is introducing something.
That system, and this is probably what you saw in that load and the current there, right? So a squared into 1 minus cos 2 omega naught t by 2. Right?
Twice the frequency.
You got twice the frequency, and now cos is just a sign shifted.
Correct.
Right? So therefore that also I can just write it as a sinusoid with a different phase. Right? So typically if you had cube here, then you would have not only the third harmonic, you will also have the second harmonic.
Yeah.
Because automatically the cube and the square terms appear in this expansion. Right? So in that sense, harmonics and fundamental frequencies always go with each other in any, not just in electrical engineering, as you saw even in mechanical engineering, that seems to be the case. Right?
But this one is not due to non-linearity.
That is not due to non-linearity. Okay. That, as I told you, is the allowed modes of vibration.
Yes.
It's, you hear the combination of all
just
of that.
for my understanding.
Exactly. Right? So that is the origin of this, and in the future lectures we'll see what amazing things we can do with this, fundamental and harmonics.
So this is a nice example for harmonics.
Exactly.
Okay,
it's a nice example that you would have done in your physics lab in some way.
The tuning fork I have done.
Yeah. And so this non-linearity is not so easy to see in physically, and that's the reason
you brought in this.
I decided to do this explanation with this violin here. In the beginning of this video, when I spoke about the sine wave, about the 220 volt sine wave, I said that the sine wave is like this, okay, and this was with respect to time, and this was the amplitude, this is v of t, and I had marked this peak value as minus VPP and plus VPP, right? And therefore I said the v of t sine wave was going to be VPP sine of omega naught t, right? Where of course omega naught is equal to 2 pi by t, and therefore this was t and this was t by 2, right? The only important thing to sort of not get confused here is VPP usually in literature is referred to as peak to peak, right? So the peak to peak voltage is usually this range. So this is VPP, okay, and therefore I should have called this as VP. This should have been VP. VPP is V peak to peak, which is equal to twice the peak voltage. So my sine wave should have actually been VP sine omega naught t, right? Of course, it is still consistent with what has been done because I used VPP just as a variable to represent the maximum value of the sine wave, but it is better to clarify this right away because you will see this VPP being used in later courses as a peak to peak voltage, right? So in the
I am
next,
able to relate.
good. Thank you. Okay.
Thank you. Thank you.
So great. So we'll thank you all. See you in the next lecture.